Okay, good afternoon everyone. So we have completed first the discrete systems and we have seen that how the wave propagation is happening through the discrete system, and now we are coming into the continuous system. So in the last class we have discussed how we can able to write down or formulate the equation of motion for a bar element. So that's a very basic form of a continuum element, and you have seen that we formed the like we have find out first the equation for the displacement field, then we have formulated from there the stiffness matrix, and further we went ahead and we calculated, like we have seen that how it can be correlated with the like the stiffness matrix calculated from how the dynamic stiffness matrix or the spectral element matrix can be correlated with the static stiffness matrix if we are calculating it for very low frequencies like omega tends to 0. So now this thing we can able to see, and we have also seen how we can able to get the natural frequencies from that. Okay, so let's start from there, like where we have seen. So you can see here, like this becomes my dynamic stiffness matrix or spectral element matrix. So in the spectral element matrix, like how we can able to perceive that. So if we think, like, what do you mean by the dynamic stiffness matrix? So if we think that we have a system like mx double dot plus cx dot plus kx that is equal to force, let's say, or like we can think that like we have a spring, we are applying the force here and here, so correspondingly there will be the displacements also, so like f1 f2 u1 u2. So normally what happens, we can write it f1 f2 is equal to, okay, so there it is something like k minus k minus k and k. So that is my static stiffness matrix. We can say that, okay, how much force we are applying and how much displacement we can able to find from there. Very simple. Now, but what is missing here? The missing thing is that we do not have any understanding of how much mass is present into it. That is something, one of the important thing what is missed. Okay, so now if we try to add the mass and damping into the picture, then this matrix will not be something similar, or we can try to see that how the type of modifications can be seen. So let's say instead of this, if we are having something like this, we have a mass here, let's say, so this is stiffness k and this is mass m, and now you are applying a force F here, F1 here, F2 here, U1 here, U2 here. How we can able to get the force versus displacement in the similar manner? Okay, we should able to get that also, and let's see how can we get it. For getting that, what can we do? We can do it in the two ways. First thing, we can write the equation of motion for the mass. Okay, so if we try to write the equation of motion for the mass, then or the free body diagram of the mass, then what are the forces applying on the mass? So mass is moving u2 amount, so how much inertia force will be coming from the mass? You should hold out, that will be the inertial force. Agreed? Great. And what is the spring force? That will be the spring force. So if I see the equation of like kinematic equation of the mass, that will be em u2 double dot plus k u2 minus u1 equal to f2. Am I right? Agreed? Good. And how much force is coming here in that node? So now think, that force is coming on the mass. So how much force is coming on the spring? So spring is giving K into U2 minus U1 force on the mass. So if I just think that mass is getting that force K into U2 minus U1. So spring will be subjected to the force in this direction. Agreed? So that's my spring. So spring will again be subjected to the force here. Agreed? Because the spring need to be balanced. Spring will have this much of force in the other direction. And how much force is applied on the spring from that direction? That is F1. So if I do the balance at that other side, so this is the balance at node 2. What about the node 1? Node 1 will be K into U2 minus U1 equal to F1. Am I right? Okay, good. So how we can able to rewrite the full thing? So you can see that now if I am going into the, means now if I taking it like, so then m omega square plus k into u2 minus k into u1, that is equal to f2. Okay, so this thing I can write it like, so what it will be? Okay, so you have seen that, like suppose once we are having like a spring, like now if we are try to have some displacement, how much force we need? So my force will be equal to k times delta. That is a simple static manner. Okay, but what is the dynamic force or the dynamic stiffness? Like suppose you have a spring and mass, and now you are trying to having a delta amount of displacement into it, and this has a mass m. Now what happen? This mass will actually get a inertia on that side, and they also having a spring force, that is k into delta. Okay, so what happens actually? You have a force F, so you can write your equation as F equal to k into delta plus this. Now you can think that now for steady state, like harmonic motion, delta double dot will be minus omega square into delta. So what can I write? K minus m omega square into delta. So now you think, what is your stiffness now? Now that become your stiffness. Makes sense. So you can see that you are having a frequency term and the mass term into picture, and that becomes your stiffness. So this is the dynamic stiffness matrix D. This is the dynamic stiffness. Suppose if you have damping here, then how it will happen? Then it will be force times k delta plus c delta dot plus m delta double dot. So you will get it F equal to k minus or k plus I omega c plus minus omega square m into delta. So you can see that now damping, mass, all those things are coming into picture in the dynamic stiffness matrix. So if you see, inherently the dynamic stiffness matrix is similar to the static stiffness, very similar. But the important point is that dynamic stiffness matrix contains the effect of mass, effect of stiffness, and how they are changing with the frequency. So static stiffness matrix, if the stiffness is constant, that will remain constant, whereas dynamic stiffness matrix will no longer remain constant, and that is frequency dependent. If the frequency is changing, dynamic stiffness matrix can also be changed. That is the important point. Now, so here we can see that this is in the more discretized manner. But once we are talking about this type of bar problem, where you can see that you are having your stiffness matrix here, like let's say this was your stiffness matrix. So this stiffness matrix, you can see it is much more complicated, and here you cannot able to directly see where is your mass, where is your stiffness, and where is your damping was not there. So where is your mass and where is your stiffness, you cannot directly distinguish them. So they are flashed inside, because if you see what is your parameters, like you can see here EA is present, so they are representing the Young's modulus, area, and L is representing your length of the beam, and beta, if you see, beta is this. So beta has what? Your mass, like rho term is there, again Young modulus is coming in the beta, as well as you are having your excitation frequency. So that full thing is flashed into a single parameter beta. So therefore this dynamic stiffness matrix is actually have, or so this type of dynamic stiffness matrix is known as spectral element matrix, because they are actually, you cannot directly get what is mass, what is stiffness. They are actually, like what you can say, like it get combined, or it makes a expression type thing happens. So here you cannot distinguish them directly. Okay, so you get this type of terms. Is that clear? So did you got that what is the dynamic stiffness matrix and what is spectral element matrix actually? Okay, so if this is clear, so now we can able to go ahead further. Fine. So let's try to do the same for our beam element and try to see that how it look like. Okay, so what is the beam element? Like if we take a member, the beam element is typically loaded in the outer plane, whereas in the bar it is loaded in along the axis, but beam is loaded transversely. So you can able to see a bending action, or the deflected profile is going like this type of way. You can see that deflected profile coming. So that's typically a beam. So in this case, what happens? We can able to see importantly we can able to see the bending. We will have the CR. We will have the rotation and transverse displacement. So these are the 4 different things we can able to see in the beam. Okay, agreed? So now let's see. So what are the degree of freedom in the beam? So in each node of the beam we can able to see the 2 degree of freedom. One is transverse displacement, maybe we can write it W, and rotation theta. These are the two displacements we can able to see, transverse displacement and rotation. In case of the bar, what was happening? Axial deformation was the degree of freedom. Now here, these are the two degree of freedom we can able to see. Okay, so associated forces are, because we know that once there is a degree of freedom, there also a force term present. Okay, so what are the forces? Shear force V and bending moment M are the associated forces in that. Okay, so what are the equation of motion for a beam? Okay, yes, so now you can see that shear and bending are the two forces coming on it. Okay, so what is the equation of motion? So first thing is that Euler-Bernoulli beam, Euler-Bernoulli beam. So in that, what exactly happening? So there we have a two prime assumptions. One thing is that plane section remain plane before and after bending, and second point, section perpendicular to the neutral axis will remain perpendicular after the bending. Okay, so perpendicular, remain perpendicular. Fine. So from there, if we derive the full equation of motion, we can get that that's a equation of motion of the domain of an Euler-Bernoulli beam. So this is the equation of motion in the domain. Means wherever you have the beam element, this equation of motion will be satisfied. Agreed? Now there is also two associated things, that is the definition of the bending moment and also definition of the shear force. So AM is coming with these are also the two associated definitions of that, like defining the bending moment, that is EI into del 2W del x2 and shear force equal to del M del x. If you do the del M del x, you will get directly, it will be del 2W del x, del 3W del x3, automatically it will become. Okay, but this thing is true for a specific sign convention, because here there could be some sort of plus and minus sign can be changed based on how you are assuming the direction of the forces or direction of the moment, like direction of the shear force or direction of the moment. So this thing is satisfying with so this is the bending moment diagram and this is the shear force. So this you can remember very easily, that is shear force is following the left up right down. So shear force SF left up right down, they are positive, and BM sagging, or you can see a smiley face, is basically positive. Okay, but it's set. The bending moment will be going like this. So that bending moment is positive. Okay, and displacement is always up and down. So displacement is invariably, the displacements are always like this. So reds are the displacements. Displacements are always like upward is positive and anti-clockwise is positive. Okay, so displacement case, like if I see the displacement, so transverse, that is upward, is positive, and rotation clockwise is positive. Okay, makes sense? This is always the scenario, because this is very important. Because why it is important, that sign convention? Because once you are actually going to join, or like sometime like we have a beam, another beam, another beam, if you are going to join this type of connections, then if you are messed up with the sign, you can get a completely wrong answer. So that's why it is very important to be careful with the sign. Now you may found in the several book that instead of this plus, maybe you will have minus. Instead of this plus, you may have minus. Instead of this plus, you may also have minus. But remember, that will alter your, of this definition will be altered. Okay, for example, instead of sagging bending moment, if you make it hogging bending moment, positive, then what will happen? Then there will be a minus sign in the bending moment. Okay, so these type of things are actually happen, but I personally found this is simple, where equation everything is positive, and diagrammatically also left up, right down for shear, and smiley like a sagging bending moment is positive. Done? Quite clear. Okay, so now this is my equation of motion. So EI del 4W del x4 plus rho E del 2W del T2 equal to 0. That's my domain equation. Very good. What are the parameters here associated with? We have W, which is basically function of space and time. Okay, and we have bending moment, shear force, displacement, and rotation. Oh yeah, there is another thing also important I missed. That is the definition of rotation. Theta is basically equal to del W over del X. Okay, so W equal to X comma T, fine. So how can we write? So first, what will be our objective to give? Our objective is to find out the spectral element. So if I try to think, if I try to find out the spectral element, what should be my objective? My objective is to write it in this form. Let's first put it here. It is my displacement is W1 theta1 W2 theta2, and if I see correspondingly if I go shear bending V1 V2 M1 M2. So you can think there is a change in direction in the M1 and the V2. You see, other things are just correlated, directions are same, but M1, you see that M1 and theta1, they are not in the same direction, they are in the opposite direction, and V2 and W2, they are also in the opposite direction. So here we need to do something, but okay, that once we will do it, we can check that. Okay, so first we don't need to be worried with this. So let's just first try to establish a correlation between W1, theta 1 and M1, V1 and try to see that how these things are coming. Okay. So let's first try to solve it. Okay. So what will be our objective? First, we can assume that solution is steady state harmonic. So harmonic steady state. So that means del 2W del T2 will be equal to minus omega square W. Make sense? Simple. We have already seen that several times because we can do it like a variable separation manner. So what can I write? EI into fourth order derivative of W minus rho A into omega square into W, that should be equal to 0. So what can I get? W fourth order minus so if I just say that this is my lambda, what can I write? Or lambda to the power 4 W. So what can be my equation of motion? So how we can solve the lambda? Or not lambda, lambda we already know. So lambda to the power 4 equal to rho A omega square divided by EI, that we already assumed. So my objective is what? To solve W, and W is not W, that is Wx basically. So Wx. So what should be the solution of Wx? If I think that Wx equal to e to the power of beta x or some value W into e to the power of beta x, can I write it? Can I write that way? So what will be the fourth order derivative of this? So that will become beta to the power 4. So I can write it beta to the power 4 W into e to the power of beta x minus alpha to the power 4 W into e to the power of beta x, that is equal to 0. Can I write it? So what is my solution? Beta to the power 4 equal to alpha to the power 4 equal to rho A W square divided by EI. So how many solution of beta we can get from here? So you can also forget the lambda, no need. Well, lambda is just like acting like in between thing. Just if we just forget the lambda. So beta to the power 4 equal to rho A omega square divided by EI. How many solution of omega we can, or sorry, how many solution of beta we can get from here? How many? 4. Exactly. What will be the fourth solution? Plus minus 1 comma I fourth root. Okay. So one case it will be 1 multiplied with 1. Another case it is multiplied with I, and there will be another 2 cases plus and minus of that. Okay. Make sense? So these are the 4 different values of beta we can get from here. Okay. Now what? We got the beta, this thing here. So what is my equation now? So I can say that W of x, this is basically W of x, what I am solving here actually. So W of x, that is nothing but C1 into e to the power of beta 1x plus C2 e to the power of beta 2x plus C3 e to the power of beta 3x plus C4 e to the power of beta 4x. Agreed? And beta 1, beta 2, beta 3, beta 4, we can get it like this way. And we can also see that these are like e to the power of. So if I just think that like this part, yeah, that part is only lambda. So if I just think that, just like think like this, so that 2 or 4. So e to the power of lambda x, e to the power of minus lambda x, e to the power of I lambda x, e to the power of minus I lambda x. We can write it. Agreed? Again what? C1, I can again do it like a cos of lambda x plus I sin lambda x. So that will be cos hyperbolic. Sorry. Yes, so that is important. Like last case we have already seen. Yeah. So that is cos lambda x plus I sin lambda, but that is wrong because here it is only lambda. So that is the imaginary of it. So it will become cos hyperbolic and sin hyperbolic lambda x. Make sense? In next case it will be plus C2 cos hyperbolic plus C3 cos lambda x plus I sin lambda x plus C4 cos lambda x minus I sin lambda x. So you can see here that we are having this hyperbolic terms here, cos hyperbolic. So this is cos hyperbolic, sin hyperbolic, cos hyperbolic, sin hyperbolic, and then you are having cos sin, cos sin. Previously, if you recall, go back to the previous case, you have only sine and cosine, not hyperbolic function. If you see that displacement field also, displacement field was sine and cosine only. No case of the sine hyperbolic, cosine hyperbolic. Why? Because we had a second order partial differential equation, so that's why we are getting only sine and cosine. But here instead of second order we are having fourth order. So that fourth order cos hyperbolic, sine hyperbolic is coming into the picture. Okay, or if you do not want to go to the cos hyperbolic, sine hyperbolic, forget them. Just simply go ahead with the e to the power thing. What is written here? That should also, or maybe this one. Both will do the purpose very nicely. No problem at all. Or else, if you want to go, we have to go with sine, cos, sine hyperbolic, cos hyperbolic. Okay, all the methods that will gives you the same result, exactly same result, provided you do it correctly. So now, if you think, we can collect all those things like cos lambda x, whatever is the coefficient, then sine hyperbolic lambda x plus cos lambda x coefficient, then coefficient of sine lambda x. So these things we collect and we put it. So, and then we can call it, maybe this is like a1, a2, a3, a4. So what happens? Now my w, if I just go to that next slide, I write c1 e to the power of lambda x plus c2 e to the power of minus lambda x plus c3 e to the power of I lambda x plus c4 e to the power of minus I lambda x. This is one way we can write, or else we can write the same thing as a1 cos lambda x plus a2 sin lambda x plus a3 cos hyperbolic lambda x plus a4 sin hyperbolic lambda x. Either of the two cases we can do. Agreed? Agreed? Good. So whatever the case we do, this has, we can write it in that form. W of x equal to n of x into unknown. What is this? Now think, what is n of x? That is it correct? I just write that expression into two matrix. Well, maybe you can say that multiplication of the two vectors. Agreed? Because this vector is 1 cross 4 and this is 4 cross 1. So their multiplication will give me 1 cross 1. But the important point is where? Important point is I am segregating all the coefficients, unknown coefficients like C1, C2, C3, C4, and I am taking all the functions in one side. Okay? Whatever is dependent on the x, I am taking it one side. Whatever is dependent or whatever is just constant, I am taking it on the side. This allows me fantastic things like, yeah, now you can see why I did that. Because this maybe we will think that, hey, what craziness. Like we have a single term, now we make it into one vector multiplied by another vector. So, but you can see now. Now this is the Wx. What will be the theta x? Remember? What was theta? Theta x is del w del x minus. So my w is nx into c. So this will be n dash x into c. So what can be my theta x? The derivative of this thing. Derivative of this. So lambda into e to the power lambda x minus lambda e to the power of minus lambda x, I lambda e to the power of I lambda x minus I lambda e to the power of minus I lambda x into C1, C2, C3, C4. You see, now it becomes so easy. Now you do not do each and every term differentiation, means differentiation you don't need to do. You can just look at, yes, where you just need to do the derivative and you are just doing the derivative there. Make sense? But now you will see the original benefit of it. Now, if you think, we have to, so now also calculate the other two things. What is the mass? What is the moment? Moment equal to EI into del 2W del x2. Okay? So what will be the moment x? There is a double derivative of it. So this is the 2 times derivative of the same thing with C1, C2, C3, C4. Agreed? Just do 2 times derivative and each and every term we were just doing the derivative. So things should be ready. Not a big deal. And whatever will be the Vx, 3 times derivative. So now let's see. So if I write Wx, that is e to the power of lambda x, e to the power minus lambda x, e to the power of I lambda x, e to the power of minus I lambda x. Okay. I'm not writing that c so many times. Instead of writing that c so many times, I'm just writing it as like c vector. So people should understand whatever is c. Okay. So what will be my theta x? We already seen. So what will be my mx? There will be I square minus minus plus. Please check that whether it will be. I think it is plus. Make sense? That is my displacement. All those things have come. What is my target? So if you think that is like W1 theta 1, W2 theta 2, V1 M1, V2 M2. We are looking for getting the relationship like V1 M1, V2 M2 with my W1 theta 1, W2 theta 2. Then it will be my stiffness matrix. That's our goal. That's the dynamic stiffness matrix. There we have to reach. Okay. In that middle, we have to eliminate C because C is unwanted thing. We do not know what is the C actually. So we have to definitely eliminate C. But elimination of the C should be with some vision. So now let's see how we can rearrange the full thing so that we can able to get there. How should we do that? So first thing is like we need this guy V1 M1 V2 M2. Agreed? So what is V1? From this set of equations, can we find what is V1? Exactly. Substitute x equal to 0. Exactly. Substituting x equal to 0 should give me V1. Perfect. So V1 is nothing but V of 0. Agreed. How can I get V2? X equal to L. All of you agree? No. With a minus sign. Why? What just I was mentioning. Once we are assuming that this is my equation of motion, this is the moment equation and this is the shear force equation, that is associated with that my shear force in the left is positive and shear force in the right, which is going downward, is positive. So that left up right down concept has to be remembered. And bending moment is also, sagging bending moment is positive. So once we are putting the shear force, first one is correct. Both the things is in the same direction. Like these two are in the same direction. But here, you see, this is going up, this is going down. That downward is my V of L. But once I am writing V2 in the above side, then V2 should be negative of VL. That is very important point. And most of the cases, people miss that and it has a lot of the complications create. Okay. So this is important point that there is a minus sign. Okay. What about the bending moment? M1 will be, and what will be M2? Minus M of 0. Perfect. And M2 will be ML or minus M of L? You can remember all whatever is the number of degree of freedom, that plus minus thing only happens that many times. That minus thing will happen only that many times. So here what is the degree of freedom? 2 per node. So 2 times the minus will happen, not more than 2. So you will have, like, once you have a 2 degree of freedom, that means state vector will be 4. So 2 state variable need to be altered. Make sense? So now think how I am writing it. I am just putting it V1, M1, V2, M2. Or I should not write it like that, just a minute. V0, V0, M0, VL, ML. EI I can take it as a common. We will have C1, C2, C3, C4, which is basically my C vector. Okay, agreed? So how can I put it? V0, this term with x equal to 0. So what can I write? Maybe I'll just write it with, so lambda cube e to the power 0. E to the power 0 means 1. Don't need to write it, forget that. Second thing, minus lambda cube. Third, I lambda cube. Fourth, I lambda. Okay. Second, I can write lambda square, then lambda square, minus lambda square, minus lambda square. Okay. Then second case, VL, lambda cube e to the power lambda L, minus lambda cube e to the power of minus lambda L, I lambda cube e to the power of I lambda L, I cube minus I lambda L. Okay, we can substitute in that VL, lambda square e to the power lambda L, lambda square e to the power minus lambda L, minus lambda square I lambda L, minus lambda square minus I lambda L. Look, we substitute the full matrix, and that matrix can be defined also, because you know what is the value of lambda for a particular omega. Check what is the meaning of lambda. Lambda is nothing but root over of rho a omega square ei, fourth root of it. Only the positive one. I am not saying the fourth root means 4 root. No, just like a do the fourth order like that root, and then rho a omega square divided by ei. Rho a ei are the property of the beam. So we know that omega is the excitation frequency. So we can calculate whatever is the lambda. Any doubt? The lambda is now known to us. So once the lambda is known to me, only one variable is remained, that is the L. L is also known. What is the length of the beam? So the full thing is known to me. So if you want to know now V1, M1, V2, M2, you already have this matrix. This vector already you have. How you get it? You can either do the transformation, that is a very simple transformation. You can do V0, M0, VL, ml, that is first stage 1 minus 1 minus 1 1. So if you just pre-multiply with this, it will do the thing, or you don't need to do that mathematics, forget it, just add minus signs here, that full thing, it will also do the same thing for you, just it will change it to a negative one. Okay, whatever the way you are preferring, you can do that, but this is more logical way of doing it, like pre-multiplying with the transformation, whatever you are transforming, so that the row column adjustment and all those things can be captured here. Okay, agreed? So if I say that this is my what type of matrix, this is my F type of matrix, Fx type of matrix, so F matrix, then multiplied by F RF matrix, or wait a minute, let's just change it, just make it, yeah, this is F matrix, F vector, this is the F vector, and this is the RF vector. So what can I say? That my V1, M1, V2, M2, which is nothing but my force vector, is equal to R F times F matrix times C vector. Agreed? F is this, RF is this, and C is this. Got it? This portion is done. Now, next thing is my displacements. How can I get the displacements? Good point is that displacement don't need to change. Displacement always, like whatever we are assuming positive, they are positive. So displacement, how we can calculate? We have Wx theta x. Here also, so how W1 will be equal to W0, theta 1 will be equal to theta 0, W2 will be equal to WL, theta 2 will be equal to theta L. Simple. So what can I write? W1 theta 1, W2 theta 2, that is equal to W0 theta 0, WL theta L, that is equal to just, if I go previously one, just to quickly tell you guys, here this thing was not equal, this thing was basically 1 minus 1 minus 1 1, which I told it RF with V0, M0, VL, ML. So you will have RF still here, then your matrix with C1, C2, C3, C4, which is C vector. So if you see that, that was my Wx and theta x. So now if you just put it, W0, that will be how much? 1, 1, 1, 1. You are putting everywhere x equal to 0. So e to the power of 0, e to the power of 0, e to the power of 0, e to the power of 0. All will become 1. Next stage, you will have lambda minus lambda, I lambda minus I lambda. Agreed? Third case, e to the power of lambda L, e to the power of minus lambda L, e to the power of I lambda L, e to the power of minus I lambda L. Here it is e to the power of lambda L minus lambda e to the power of minus lambda L, I lambda e to the power of I lambda L minus I lambda e to the power of minus I lambda L. So that we will get. So if I say that that is my F matrix and this is my D matrix, so I can say that my force, and this is my D vector and this is my force vector. So my force vector is equal to Rf into F into C, and my small d equal to capital D into small c. Agreed, all of you? So what is my target? My target is to F something like K into D. That's my objective. So what I have to, and that C is something like unwanted. So I can write this one, D inverse of this, and I can substitute that full thing here. So I can get so that's nothing but my K matrix.